Can you hear me? Okay. Good afternoon, everyone. Today I'm going to talk about PETSc and PyTorch interoperability in this mini tutorial. So a lot of people have been interested in integration between simulation and machine learning. Traditionally, one could generate a lot of training data by running your simulation code again and again. So this involves saving your simulation results to files and loading the files in the classic ML framework, such as PyTorch or TensorFlow. An alternative method is to rewrite your simulation code entirely into a machine learning framework. And these approaches are inefficient and annoying for both computer and human. So the question is, can we do in situ machine learning for existing simulations without heavy development efforts? We made this possible using PETSc. We can actually combine PETSc and PyTorch into a single Python-based workflow that allows us to do a few interesting things. We can embed machine learning into simulation. So for example, we can replace part of the simulation with some neural networks. And we can embed simulation into machine learning as well. A typical example for this application is a neural ODEs. In addition, we can leverage automatic differentiation from PyTorch when using PETSc. Or we can also leverage a state-of-the-art numerical solvers in PETSc when we are using PyTorch. So this mini tutorial will cover 3 specific topics. So hopefully these topics can help you get started with making your applications more intelligent by incorporating the power of AI. So in particular, you...
sorry for interrupting. Could you unmute on the Zoom?
Oh, sorry.
Thank you.
Okay. So in this mini tutorial, you'll learn how to convert between PETSc vectors and matrices and PyTorch tensors. And you'll learn how to generate Jacobian with PyTorch and use it in PETSc. And you'll learn how to use PETSc and PyTorch for solving system of ordinary differential equations and training neural ODEs. So we know that PETSc is built upon vectors and matrices. PETSc has no concept of tensor. And PyTorch is built upon the concept of tensor. So how do we make PETSc talk to PyTorch? So the technique we rely on is called DLPAC, which is a protocol for converting tensors across different tensor libraries. So basically, DLPAC allows you to use PyTorch tensors in TensorFlow, or you use TensorFlow tensors in PyTorch. So in PETSc for Py, we provide APIs that allows you to convert PETSc objects into DLPAC objects, which is essentially a stepping stone between PyTorch tensor and PETSc objects. DLPAC contains a bunch of auxiliary information, such as the shape of the tensor, the location, the device information of the tensor. And by using DLPAC, we can do zero-copy in-place conversion. So we are not allocating new space for the tensors converted from other libraries. So everything is happening in place. So if you're doing your simulation on GPUs, the conversion will happen on GPU. If you're using CPU, the conversion will happen in CPU. And when you're using these APIs in PETSc for Py, you can pass a DLPAC object, or you can pass a tensor object directly. I'll show how this works. So let's look at this piece of code. So first, we create a PyTorch tensor, which is a rank 2 tensor that contains an array of 1, 2, 3, 4. Then we create a PETSc vector out of this PyTorch tensor by calling create with DLPAC. Then we try to modify the last elements of this PyTorch tensor. And we try to flip the sign of the last element, which is a 4. And now we print out both the PETSc vectors and the PyTorch tensor. As you can see from the output, so both the PETSc vector and the PyTorch tensor give you -4 in the output. So as you can see, if you modify the object either in PETSc or PyTorch, and the modification will be reflected in both places because the two objects are actually sharing the same memory. And similarly, we can also convert PETSc vectors to PyTorch tensors. So here we first create a PETSc vector by using create with array, which also has four floating numbers, 5, 6, 7, 8. Then we attach some DL pack information to this vector because so the native PETSc vector doesn't know any information about the tensor. It doesn't know the shape of the tensor, right? So DL pack information somehow tells the PETSc vector what the resulting tensor should look like. Then we convert this PETSc vector to a PyTorch tensor by using the from DL pack function, and then we print this tensor out. As you can see that this vector is shown as a rank 2 tensor in PyTorch. And now I'm going to show you how to leverage the automatic differentiation from PyTorch. So this is quite simple. The first we created a Jacobian matrix with mat shell, and then you need to implement your own mat mult operation. In this mat mult function, you need to produce the product of the Jacobian matrix A with an input vector x. And this can be done by evaluating the right-hand side function once, then calling PyTorch's autograd function. And finally, this Jacobian can be passed to PETSc for solving implicit systems. And let's look at the code. So here is a implementation for the shell Jacobian matrix. In this mult function, we first convert the PETSc vectors to PyTorch tensors. Then we enable the gradient calculation for a cached U tensor. This cached U tensor actually stores the system states. You can actually do the caching in your RHS function implementation. Then you call your right-hand side function, which is called func.ex here. Then you do an autograd gradient function call. And finally, you can copy the output back into the PETSc vector. And here's how we created this shell matrix in PETSc for Pi. Stefano will talk more about PETSc for Pi tomorrow. The shell matrix in PETSc for Pi works slightly different from the C implementation. So in the PETSc for Pi version, you need to specify the type of the matrix to be Python, and then you set up the Python context. And then you set up the matrix and assemble the matrix and set the Jacobian matrix to a TS solver or some other solvers in PETSc. Next, I'll show you how to solve a system of ODEs using P-node. The P-node is actually a neural ODE implementation based on PETSc for Pi and PyTorch. As an example, we consider the Robinson's equation, which is a very simple ODE system. So here, this ODE system contains 3 components. U are the concentrations for 3 species, and K are reaction rates. So let's look at the code directly. In this implementation, the right-hand side function is implemented by inheriting from the PyTorch's neural network module. And this should look very familiar to PyTorch users. In the forward method, you implement the right-hand side of the ODE system, and you can specify the parameters of this neural network to be just the reaction rates. So note that PETSc can not only solve the ODE system for you, but also perform sensitivity analysis. The PETSc TS adjoint solvers are capable of calculating the derivatives of a quantity of interest with respect to system parameters. The P-node actually encapsulates both the PETSc time-stepping solvers and TS adjoint solvers. So as users, the only thing we need to do is just to provide the right-hand side function for the ODE and store the system parameters in a gradient-enabled tensor, as I showed you in the previous slide. And finally, you just need to define the quantity of interest, which is usually a loss function when you are doing a machine learning task. So some of you may ask, why do I use the adjoint methods here? Because theoretically, you can actually implement your own ODE solver in PyTorch and backpropagate the entire ODE solver to get a gradient, right? So the adjoint methods in TS adjoint actually can allow us to avoid backpropagating the entire ODE solver, at the same time maintaining the same level of reverse accuracy as automatic differentiation, but be much more memory efficient. So for the sake of time, I cannot show you the advantages of using PETSc TS adjoint in this mini tutorial. I'll just show you the code directly. So in this code snippet, we start from defining the initial state of the ODE, and we define the right-hand side function, and we created a solver, the PETSc adjoint solver, and set up this solver by passing the initial states, the right-hand side function, the step size, the method. So we're using Crank-Nicholson for time integration here, and we enabled adjoint calculation. And then we call the adjoint solver to get the predictions, which is actually essentially the solution of the ODE. Then we can visualize these solutions. Then we can define a loss function, which is nothing but the maximum absolute error between the prediction and the ground truth. And finally, we call the backward function for the loss function. So note that we're not backpropagating the entire ODE solver. So under the hood, this backward function is calling PETSc TS adjoint solver to calculate the gradient of the loss function with respect to the system parameters you specified. So these plots shows the solution of this ODE. And as you can see, the only thing we provided is just the right-hand side function implementation. So the Jacobian, or the action of the Jacobian, is calculated in a matrix-free way by P-node. So finally, let's go one step further. Let's talk about neural ODEs. For neural ODEs, we assume we don't know the right-hand side of the ODE anymore. The right-hand side of the ODE is actually approximated by a neural network in this neural ODE approach. And so here we define a neural network with 5 hidden layers, with 5 nodes per layer, and an activation function of GELU, which is a fancy version of the ReLU. So GELU is known to be better than ReLU when approximating complex dynamical systems. So now you can see that this right-hand side function is essentially approximated by a neural network. And again, we define a PETSc adjoint solver, we set up this time-stepping solver, and in addition, we pick an optimizer from the PyTorch. So my favorite optimizer from PyTorch is AdamW here. Now we can start the optimization loop for training. In each iteration, we first get a batch of data, and we zero out the gradient for the parameters to be optimized. Then we call the PETSc TS adjoint solver to compute the prediction. And then we calculate the loss function, which is MAE between the prediction and the ground truth. And we do the backward just like before. And finally, we call the step function from the optimizer to update the parameters during each iteration. After training for a few hours, you should be able to see the results. And here I'm going to show you the results directly. And so here we show how the prediction matches the ground truth. We actually use the two different time integration methods. We tried Cranker-Nicholson and adaptive Doppler-5. And as you can see here, the implicit methods work much better than using the explicit methods because we are dealing with a very stiff dynamical system. Using adjoint-capable PETSc time integrators is actually the key to achieving performance for this particular problem. And one can actually fine-tune the linear solvers, nonlinear solvers, and checkpointing for adjoint calculation with command line options without changing your code. So this is very PETSc style. And this is a perfect example for demonstrating how PETSc and PyTorch work together with minimal conversion overhead and full GPU support, and more importantly, mini batching support. So note that we are not solving the ODE system once at each time integration, in each optimization iteration. So in each optimization iteration, we're actually solving the ODE system for a batch of data. So for example, multiple initial states, and we get the output at the same time for all these different initial conditions. And here are the sources for more information. Thank you. I will make the slides and a notebook available so that you can run the code in these slides.
Thank you very much, Zhang. Yeah, so the code cells that you had there, that was actual PETSc for Pi that you can execute and run the Jupyter notebook, right?
Yep.
Awesome. So at 45 minutes, we are going to have a coffee break, but I think we have time for a question before we all disperse, if anyone has a question for Zhang. So I think this talk goes well with Barry's opening talk. I think it's great to see this kind of interoperability between the ML frameworks and what we've been able to do with solvers to combine them both for kind of the best of both worlds, as he showed. Your experience with building these tools, is there anything that you feel like PETSc needs to be doing better to improve that interoperability experience?
Okay, so very good question. So I would say the most tricky part in the implementation of neural ODE is how to support mini batching. Because mini batching, that's the core of machine learning, but it's very rarely exploited in classical numerical solver libraries like PETSc. Because we're so used to solving the ODE or PDE system with a single initial condition. If we have to do uncertainty quantification, we may generate a lot of samples, but we essentially do these multiple simulations one after another. So I think that's a major difference between classical numerical simulation with machine learning, which is centered around mini batching, the idea of mini batching. And we have to do a lot of work to make PETSc solvers compatible with the batched solve.
Very good point. All right, everyone, that will conclude our first session of the afternoon. The coffee should be refreshed and available in the back room, and we will meet back here at 3 o'clock for our second session. Thank you all for your attention.